welcome to another lecture. We're going to do an example on designing a tension member in steel. When we're looking at that, let me show you this piece of steel here. Let me fix this steel. Okay, so we got this angular iron. And if this angular iron was subjected to a tension, assuming it's connected to, it's using a cross frame on one end and the other end, and it's connected, so it's in tension, it's being pulled apart. There is two primary things we worry about. One is failing through gross cross-sectional area. That means if you pull it apart hard and look at this cross-sectional area, and you basically go beyond the yield strength. This is a 50 KSI steel, so if you go beyond 50 KSI, you basically fail the other way. And the other one is failing through net area. The net area is if I have a hole in here and these hole bolted connected to the other member, now I have a net area and it's going to rupture through these hole. Those are two primary members we worry about. Let me show you the PowerPoint right here. So just as I explained it right here, two primary locations in a member, a gross cross-sectional and a net cross-sectional area. And then one of the limitations we're going to look for is make sure our cylinder limit will not go over 300. And normally all tension member, you don't have to worry about buckling, but you really don't want to go over 300 here. And then the failure mode happen in a tension member. I have other videos on like a gusset plate design. We look at the tensile yielding, that's based on a gross cross-sectional area. Then we can look at the rupture, and then if you get into the connection design itself, you look at the shear rupture, bearing failure, and block shear rupture, and how it goes through that. But we go through an example. We're going to go through some of these steps. We put this right here into a ChatGPT. Said, can you look at this? And it was funny, it did it. Let me show you. It came back and it says, okay, thought through 12 seconds, and here's a clean note version of it, and did a good job explaining how to go through all these steps. There's another one. There's another. It took 5 slides to basically fill it up. But look at this example. We're going to do this example right here. And we have this member right here. It's a W8. We don't know what size, but just we know it's going to be W8. And we have two hole on top right here, and these are 3/4 inch bolt. And if you look at the member itself, is about 25 feet long, and each holes are about 3 inches apart, and the edge distance is 1.25 inches. The dead load is going to be 30 kips, and live load is going to be 90 kips. So we're going to go ahead through this, see if you can design this member. Okay, so we have, this is what we have, and let's go ahead and, we said W8, let's go W8 by 21. Okay, let me write this down. Oops. Lock this. Try W8 by 21, and then we're going to go to the manual right here, and from table 1. We get all the information, which I've already got it. I'm just going to write it down, copy it. Gross cross-sectional area is 16 inch square, and then B of the flange is equal 527 inch, and TF flange thickness is 0.4 inch, and D, it's going to be 8.28 inch, and then finally RY, it's going to be 1.26. Because this we're doing a tension member, we need to find out what y bar is for W 8 by 20. So we're going to go ahead and correspond to the WT shape. For W 8 by 21, that will be W4 by 10.5. So basically this will be half, be 4 and 21, and make them 10.5. And then if you go to the table 1.8, we have, let me shut this down. Table 1.8, we have basically for WT, this is, I'm gonna fix this, hold on. That's a WT. So WT 4 by 10.5 has y bar of 0.831 inches. Okay, let me switch screens so I can go to a bigger screen here. All right, the first thing we're going to do the load. So the load were, if we go load resistant factor design, that will be PU is equal to 1.2 times dead load. The dead load was 30 kips times 30 kips plus 1.6 times life load was 90 kips. So that comes out to be 180 kips. If you don't know anything about the load resistant factor design and Albert stress design, please, before watching this video, watch my other video, compare both of them and explain what they are. This is used as a different factor for the load, and that's an old-fashioned way you just add them all up. So this will be PU, this will be PA. They are two different design, two different ways, should get the same result. And so do not ever mix these two. We're going to do it both way here. So PA is 30 plus 90, and that's 120 kips. So if I'm using this method, the load I'm going to be on this steel is going to be 180 kips. But if I'm using that method, the load's going to be 120 kips. But just because this uses a different resistance factor with that one, and it's kind of even this out. This is a little bit more conservative. Anyway, so now we have done that. We said there was two primary area we worried about. One was the tensile yield, and the other one was the tensile roughness. So let's go ahead and just worry about tensile yield. So we're going to go ahead and look at the tensile yielding, and from here we're going to go to table 5.1. So if you go to table 5.1, 5A, available strength in axial tension, this is a FY50, FU65 for W shape. Our number was W8 by 21 right there, and which is the gross cross-sectional area 616, allowable stress design 184 kips, and 277 for load resistant factor design. Now pay attention here. If you go up to the column right there it says AG, can you see that? Equal 0.75 AE equal 0.75 AG. If our is going to be equal or bigger, then we can use this table. If not, then we have to go to section D2. Okay? Pn is equal 277 kip, and this is bigger than 180, so we passed yielding. That's not going to fail this way. And if we go into the same table, look at there, and it's going to be a Pn divided by omega, and that's going to be 184 kips, which is bigger than 120, and we kind of pass both the yielding passed. Okay, that was one area we're worried about. The second area we're going to worry about is a tensile rupture. We're going to assume AG over AE is going to be more than 0.75. And then we're going to go ahead and go to table D3, look at the case number 2 and case number 7, and to find the shear lag reduction factor U. And then we have to make sure we follow the same based on, please go ahead and read that table D3, the page before and page after, and explain what I'm talking about. And one of the limits we have to find out that we're not going to be, we're going to take the maximum value, whatever we're going to find. And the table also says that, I'm going to put on a board here in a minute, it says for the cross-section you need not to be less than a ratio of the gross cross-sectional area of the connected element to the member gross cross-sectional area. So basically saying that U is equal 2 times BF. And we're going to make sure that U is not less than this. Let's figure this out. This is going to be 2 times BF. BF was, which I had it before, 2 times 5.75, and TF was 0.4 divided by the gross cross-sectional area was 616 inch square. So that gave us 0.684. Then we're going to go in the table, look at the other two. Okay, so we're going to look at the case, let's look at the case 2 based on W shape. Let me write this down here. Case 2 based on WT shape. And remember, we said this, our let me go ahead and come in here. We said our W (8 by 21), which correspond to 2 WT, would be 4. 21 divided by 2 would be 10.5. So 2 of these. And we're going to find the U of 2 of these. And that's what we're going to work on case number 2. Take a look at the case number 2 while I write this thing down here. A bar is equal Y bar, which is kind of nice. And that's equal 0.831. And then from there we can go ahead and calculate U, which is equal 1 minus X bar divided by L. L is the shape of the, L is the length of the connection. Let me write that down. L is equal length of connection. All right, so we have equal 1 minus X bar came out to be 0.831, and divided by L. L gonna come out to be L is going to be 9 inch, and if you remember, so was the 3 at 3 inch was equal 9 inch. So that's what the 9 inch comes in. And here U comes out to be, if you do this calculation, 0.908. 0.908. That was case number 7. And if we go to case number 2. So let's go ahead and look at case number 7. Case number 7, our BF, which came out to be 527. And then we have 2/3 of D. And that's going to be 2/3 of D was 828, 8.288. And that gave us 552. We need these numbers. You notice that BF is less than 2/3 of D, because 527 is less than that, and because it's connected to 3 lines, and look at that code, because of that, and therefore our U, it says U is equal to 0.85, and I'll repeat that. And now we have 1 U is equal to 0.85, 1 is equal to 0.98, and the other one came out to be 0.684. So this one will control right here. I will control, the largest one will control. Okay. Well, now we have the U kind of figured out. This is the reason we're using U, because of a net cross-sectional area. The yielding, which we did right here in the past, was based on gross cross-sectional area. This is going to be based on a net cross-sectional area. Why we didn't calculate Fy times G? Because the table 5.1 did all those calculations for us. You don't have to calculate. So we're going to go through more tables. So okay, we're going to go ahead and calculate the net area. Net area is going to be gross cross-sectional area. We got 4 holes, 2 on top, 2 on bottom, and multiply the diameter of the hole plus 1/16 times the thickness of the plate itself, which is the thickness of this flange right here. So it's going to be, the AG came out to be 616, and that looks okay. 616 minus 4 times DH was 13/16 plus 1/16, so that makes it 1 inch basically, and time 0.4, and that will give us 476 inch square. Now we can calculate AE. AE can be calculated, and using different colors so you can, I will not be mixing. AE, the color shows up, okay. So AE, it's going to be basically AN time reduction factor U. AN is a 476, 0.908, and that will give us 432. 4.32. At the beginning we talked about AE divided by AG. Let's go over that. AE divided by AG, it's a 432 divided by 616, and that will give me 0.701, which is less than 0.75, and so we did our assumptions. We said it's going to be more than, but it actually came out less than that. Now, this is kind of important. Pay attention to this. Because this is less than 0.75, we no longer can now use table. Let me write this down. We cannot use table 5.1. So table 5.1 is not valid. Okay. We're going to have to go to section D2, do it. Let me erase the board, we can do that. Okay, since AG is less than 0.75, we're going to use section D2, and that basically says that PN is equal FU times AE, and FU is a 65 for 50 KSI, and AE, I erased it, it was 432 times 4.32, and that will give us 281 kips. Okay, so now we got that, and then we can go ahead and do the same thing here. And do it in both allowable stress design and load resistor factor design. And then here will be phi is a 0.75 for rupture. So now we're going to have phi times P/N is equal 0.75 times 281. That comes out to be 211 kips. And what was it before we erased it? The load was 180. Look like this might control because there's a small margin. And then for this one, omega is equal to, and then we're going to have P/N divided by omega is equal to 281 divided by 2, and that's going to be 141 kips, which is bigger than 120 kips. Really, this is control. The yielding that's going to control, because if it's going to fail, it will fail through rupture, not yield, because yield had a bigger margin. But there's not a limit. We've got to look at the slenderness ratio. What's L over R? Let me do this in different color because I'm color happy. I don't know. And that was 25 feet, the length of the member. Let's multiply by 12 divided by R. R was, at the beginning we talked about it, it was 1.26. And that will give me 238, which is less than 300. And we check this one out. Okay, so briefly going over it, we had the member. We checked it for yield, we checked it for rupture, and it passed both of them. So the member, it's okay in tension, that member that we picked. And but this is control anyway. I hope you liked this, and if you liked it, give it a thumbs up. Thank you.